Replacement rules. Hi, did someone say replacement rules? Yes, that's what we're doing today. They're not a new and different strategy by which we determine the validity of an argument. Rather, they go hand in hand with rules of inference. It's fair to say that they're ancillary to rules of inference. They supplement the rules of inference, though, of course, they could never replace them. It is possible, and by now you have done plenty of examples showing how, it is possible to run an entire proof using rules of inference without the replacement rules. But now and then, a step is called for in a proof that the rules of inference alone could not handle or could not handle easily. Okay, so the rules of inference plus the replacement rules that we're covering today provide the full complement of rules with which you should be able to handle any direct truth functional proof in what is one of the things that's normally called natural deduction. Now, when I say that, when I say you could construct a number of proofs using just the rules of inference, although you can do more using them together with the replacement rules, a question naturally invites itself. That is, could you do proofs with the rules of inference? Could you do proofs with just the replacement rules? Well, it depends on how broadly you define a proof. I mean, if you take a proof in the vacuous sense, in which anything proves itself to be true, given A, you can deduce A. Well, yeah, in that case, you can really work with a minimum of rules. Could you, and let's use the word non-trivial in a kind of casual sense, an everyday sense, everyone knows it when they see it. Could you arrive at non-trivial, informative proofs using only replacement rules? There, I have to say, I can't think of one. You might prove me wrong. You might come up with a very interesting kind of proof, and lo and behold, that proof uses only replacement rules and gets us in an interesting way from one point to the other. But this intuition, going from one point to the other, is what I want to zero in on as demonstrating one of the differences between rules of inference and replacement rules. My metaphor last time in connection with rules of inference was of walking. Not just any walking, because we walk all the time, we're logical all the time. But when we try to show how we are being logical, we walk like toddlers navigating their way across the room. But still here, we have this idea that we're arriving someplace. We're starting with the premises and we arrive at the conclusion, and the conclusion says something different from what the premises had said, at least on the face of them. Can we give a more precise sense to this intuition that the conclusion says something different? Yeah, well, here's one way of putting it. You start with a group of premises, normally, and you use some combination of rules, inference rules plus replacement rules, and you arrive at a conclusion. And you know what? You cannot normally go back, starting with the conclusion, to derive the premises. Now, that's more than just a hand-waving intuitive sense of arriving at somewhere new, right? I'm saying that you can start with the premises and arrive at the conclusion, but not vice versa, normally. And this fact about the typical proof, the typical derivation, brings us to one of the two important differences between replacement rules as we use them and rules of inference as we use them. you recall that I said last time, or if you don't recall, please bear it in mind now, that rules of inference are unidirectional. If you use a rule to get from line 3 to line 4, you cannot use that same rule of inference to get from line 4 back to line 3. So for example, if you have the conjunction A and B, you can use the rule of inference we call simplification to get to A alone. You can't just help yourself. You can't go from A alone back up to A and B. Can't be done. They're unidirectional. By contrast, rules of the replacement rules are bidirectional. They're like double-edged rules of inference. They're written, for example, well, they're written with these 4 dots. So if we have P, and here we have P and P, that's one of the simpler replacement rules, although most of them are simple. And it's a notable fact about this replacement rule that as you can replace P with P and P, so too can you replace P and P with P. Again, and now I'll say something that was just as true of rules of inference and is true of all replacement rules. Where I've got P here, I can put naturally not only any other letter, but also any other formula, however complex. I'm saying that a given formula, long or short, simple or complex, is equivalent to that same formula conjoined with itself. Equivalent to means either one can substitute for the other. You can infer backwards and forwards. The difference at stake here is like the difference between the conditional, the if-then, and the biconditional, the if and only if. A conditional statement, if P then Q, gets you from P to Q. Once you have P, then you can get to Q. The biconditional P, if and only if Q, tells you that if you've got P, you've got Q, and if you've got Q, you get to P. All right, so the replacement rules are like biconditionals compared to the conditionals implied in any rule of inference. Now, this is a significant difference to bear in mind, although in practice, it might not make all that much difference. We don't normally reach the end of a proof and say, fantastic, now let's turn around and take it back the other way. We're still entering a proof with the purpose of starting out with those premises and getting to the conclusion, not starting out with the conclusion and seeing how far we can get back to the premises. If you'll pardon the analogy, if inference rules are like the rules for deboning a chicken, replacement rules are the kinds of rules that would let you debone a chicken and then turn around and put the bones back in to the chicken, which is a kind of skill there's usually very little demand for. The second difference between replacement rules and rules of inference brings us back to my original characterization of rules of inference. Rules of inference, as you recall, can only be applied to an entire line in a given proof. If the entire line is, let's say, a disjunction, then it's eligible to be used in a disjunctive syllogism. If the entire line is a conjunction, then it's eligible to be used with an example of simplification. All right, but it has to be the entire line. You can't go digging around something within parentheses in a larger formula and apply simplification or modus ponens or any of the other rules of inference to that one part of a formula. Something very different is true about replacement rules. replacement rules can be applied to an entire line or to any subset of that line. Okay. Again, that's because they're identity statements. All replacement rules are identity statements. You can look at them as definitional statements. Okay. So you could, for example, go through a book. You know, you're reading a book and you think, you know, I never want to see the word triangle again. And so you replace it with three-sided geometrical closed figure. Okay, and everywhere you see a triangle, you cross it out and you write three-sided geometrical closed figure, right? You're preserving the truth of what you say because you're still talking about the same figures. You're simply replacing the word. One of Frege's examples doesn't work exactly, would be to replace, I think he said horse with steed, right? You go through and you think, I've just heard the word horse too many times in my life. Now let's take it out and put steed in, right? And then you have a change of heart. You say, I'm going to go, and everywhere I see steed, I'm going to put horse. That's an inexact analogy. It's going to be inexact for any two words in a natural language. But you get the picture, and you can do this in an exact, precise way in logic because you really do have the identity of two formulas. And where two formulas are identical, they can always be replaced with one another. So suppose you have if A, then B or C. Because A is identical with A or A, right? You can make this A, or if A or A, then B or C. Or indeed, you can make it A and A, then B or C. You can make this, yeah. And as I said, that's not true only of the single letters in a larger formula. It's also true for any part, any formula that's part of a larger formula. So you start out with if A, then B or C. And you can make that if A, then B or C and B or C. Okay. And of course, back again for where replacement rules are concerned, you can always put the bones back in the chicken. You can always put the apple back on the tree. Let's go through the replacement rules. 10 of them given in the book. You could amplify the list. You could condense the list in different ways. Often that's a matter of nomenclature. I'm not going to treat all these replacement rules equally. Some of them are simple and are so obvious you almost can't stand to describe them, let alone discuss them. And in practice, I confess, I don't always know when I put them to use. When they're very simple, I sometimes forget, I'm being honest with you here, to indicate that, for example, I'm using double negation when I see an A and I treat it as the negation of A. I try not to. I'm just saying, I sometimes do. All right. In logic, and again, Maybe not some ways in real life. We're not going to worry about that. Given how precisely we have defined negation, in logic, it's the case that any statement is identical with, can be replaced by the negation of that statement. Right? There's no surprise there. Logic has commutative laws and associative laws, just as arithmetic does. And this is, the analogy is helpfully explained in your textbook down to a specific. Just as in arithmetic, commutative laws apply to both addition and multiplication, though certainly not to subtraction or division, but just as they apply to both addition and multiplication, as associative laws also do, so too in logic do the commutative and associative laws apply, and apply equally to disjunction and conjunction, to the or and the and. But careful, careful, a word of caution. They apply when all you've got is an or they apply when all you've got is an and. They do not apply when you start mixing ands and ors any more than the arithmetic rules necessarily apply if you start mixing plus and times. Okay. P and Q is the same as Q and P. P or Q is the same as Q or P. I commented on this fact. When we define those terms, you can see from working them out on truth tables that there's no difference. This is one of the rules. Again, I'm just trying to be honest with how they get used in most people's actual practice. Most people, when they come across a P or Q in a given line of a proof and they need a Q or P, they may be, shall we say, they may be forgiven for going directly to the Q or P from the P or Q, because so little doubt arises, so little confusion takes place. Now, needless to say, this does not apply when your connective is an if-then. You can't go from if P then Q to if Q then P. You can go from the biconditional, but you can't go from the conditional to the commuted version. All right, so especially in light of the analogy with arithmetic, these are familiar patterns. So are the associative rules. And I remember in 4th grade learning the associative rules, or learning that word for the associative rules of arithmetic from my 4th grade teacher, Mrs. Harsh, who compared it to coming into a room. If the 3 of you are coming into the room, it doesn't matter if 2 of you come in first followed by 1, or the other 2 come in followed by the 3rd, right? And ever since that analogy, I have kept it in mind. Maybe P and Q walk into the room with R close behind, or maybe P comes in trailing Q and R, okay? It's just a matter of how we group them. Could we indeed do without the parentheses altogether in a case like this? In a case like this, we could. The parentheses really are extraneous. I mean, in a tight logical sense, they're extraneous because they have no effect on the truth value. Now, again, this is only true when all you've got, as in this example, is conjunction, or when all you've got is disjunction. It is not true once both disjunction and conjunction start showing up in a single formula. We're going to get to that later when we do distribution. Distribution, unlike the associative and commutative rules, distribution is not obvious. Distribution is not trivial. Distribution, some people find hard to remember, none of which you would say about this, okay? So for example, I'm now going to change that conjunctive sign to a disjunction, and I predict that you are all just as surprised at this associative rule as you were at the associative rule having to do with conjunction, which is to say, not at all surprised, all right? The best way to think about it is what I said a minute ago. Strictly speaking, the parentheses are irrelevant. They have no bearing on truth value. Here's another quite straightforward, quite unsurprising rule: duplication. And as the commutative and associative rules also do, duplication applies equally, or you might say it has a sub-rule for conjunction and disjunction. You know, if you want to call these two applications of the same rule or two different rules, nothing, it doesn't matter at all. Nothing changes in the universe. P is equivalent to P and P. P is equivalent to P or P. You can conjoin or disjoin at will. You can reverse the process. Why would you want to go from P to P and P or to P or P? There aren't a lot of situations in which you do feel that need. What happens more often is that you're in the opposite situation. You've got the duplicated statement and you want to simplify it to the single letter, right? And if the makers of that fine candy, M&M, had been aware of the duplication rule, they would have thought, oh man, you know, this is a pleonasm on our part, M&Ms. They should have just called them M's, okay? But at least logic shows us by the replacement rule that the two statements are equivalent. One word of caution here, one word of caution. I said that this works for disjunction and conjunction. Watch out. It does not work for the horseshoe. It does not work for the conditional. Why is that? Well, look at it this way. Take P and P. Is it true or is it false? Trick question. P and P is true if P is false. P and P is true if P is true. P is true if P and P is true. They're true at the same time. They're false at the same time. Likewise here. If P, then P, however, is always true. That's a true statement. It's a tautology. It's always true even if P is false. So you cannot replace P with if P, then P, because then you'd be replacing a proposition that could be either true or false with a proposition that's always true. You can't do that. De Morgan. Again, there are two rules, and some people, funny people who do logic, refer to them as De Morgan's law and De Morgan's other law. We won't be funny here. When you negate a conjunction, you get the disjunction of the negations. Is it like multiplying through? Yeah, it's a ton like multiplying through. Don't use that language. We're not doing arithmetic. This is logic. But yes, it's going to look just like that, except, and this is why you have to bear in mind the difference between arithmetic and logic, except that the sign changes. If you negate the conjunction, you get a disjunction. And, as you might expect, when you negate a disjunction, you get a conjunction. The two versions, the two De Morgan's laws, are identical with one another. Right? Wherever you see an or in one, you replace it with an and where you see an and, you replace it with an or. Okay. So De Morgan's rule, not P and Q is not P or not Q. Not parentheses P or Q becomes not P and not Q. And of course, you can go in the opposite direction. And now I suspect that for the first time, you might feel as though we're learning something that's not absolutely trivial. You might have had to think about this in order to come up with De Morgan's laws. I have no doubt that you would have come up with De Morgan's laws, right? But you would not have come up with the commutative and associative and the double negative laws because they're so simple, you wouldn't even have set out looking for them. How can you find that which you do not seek? Okay, well, that's philosophical. Now, so far, you may have noticed, we've only spoken of replacement rules involving conjunction and disjunction. Let's spread our vocabulary a little beyond those connectives and talk about conditional and biconditional. The rule with a really Zen abbreviation, B. Who wouldn't want a rule like that that's all about being? BE stands, of course, for biconditional exchange. P, if and only if P, may be replaced by the conjunction of if P then Q and if Q then P. So finally, with this, our sixth replacement rule, we've gone beyond conjunction and disjunction to speak of the conditional only, I'm afraid, in order to say something absolutely obvious and trivial about the conditional, which is the biconditional is two conditionals. P, if and only if Q means if P then Q plus if Q then P. Okay. It's straightforward. Sometimes you do need to take a biconditional apart. Sometimes you do need to take two conditionals and put them together into a biconditional. By contrast, the next one is not quite as obvious. And I say this because most people, when they're introduced to the contrapositive or to what's called the act of contraposition, might need a minute to process it, and then we'll take another minute to appreciate it. I know that was true of me, and some of you may recall back in the second week of our class when the contrapositive came up. People thought, oh, contrapositive, that's very interesting. Okay, to me, it always seemed like one of those slick wrestling moves where the wrestler suddenly turns around and has recreated the same position with their opponent. If P then Q is equivalent to, may be replaced by, or may replace, if not Q, then not P. If P then Q, if not Q, then not P. There's something elegant about it. It may remind you of modus tollens in some way. Or, well, you could, another way of saying it is, if you had modus ponens and you had the contrapositive rule, strictly speaking, you would not need modus tollens, right? Here's what I mean. Now, from if A then B and not B, we can immediately derive not A using modus tollens. But if we did not have modus tollens as a rule, here's something else we could do. Right? From if A then B, we could go to if not B then not A by contrapositive. And then coming back to the second premise, from lines 2 and 3 and using modus ponens, we would get the negation of A. Okay, so the contrapositive, not a huge surprise, still has something, to my mind, elegant and interesting about it. This example I just did, by the way, showing that we could achieve with modus ponens plus the contraposition what we would otherwise achieve using modus tollens, is a good time for me to draw attention to a very common observation people make in logic and in proofs. There are often, even in simple cases, many different ways to the same conclusion, many different paths. Normally, we prefer the shortest possible path. It may be sometimes that a slightly longer derivation is clearer or easier to remember, sticks in the head, seems to show us something more significant about the proof in question. But normally we seek the simplest proof where that simplicity is measured by brevity, okay? So the real reason we would not do this proof with modus ponens plus a contrapositive is that we've got modus tollens. Doing it with modus tollens makes it that much shorter a proof. Now, the conditional exchange is also something that has surfaced. If you watched the lecture for 2B, the more extensive review of translation into logical language and truth tables, you would see that that subject comes up. A material conditional may always be translated into a disjunction with the antecedent negated. Not both of them negated, just the antecedent. And that's a way, incidentally, that's a way of reminding yourself why a conditional is not commutative. Or statements are commutative. They can be turned around, and statements are commutative. But the conditional exchange, the translation of a conditional into a disjunction reveals the asymmetry. Yes, this can become a disjunction, but only if you negate the antecedent. This is not a bad time, incidentally, to repeat something I've said about how these replacement rules are applied. We don't have to apply them only to single letter propositions. So, for example, suppose we have the conditional statement, if A or B, then C. That becomes not parentheses, A or B or C. And then, of course, you can use De Morgan's law. And make it parentheses, not A and not B or C. Can we do anything else? Yeah, we can distribute. Going to get to that in a minute. The difference is, as you'll see, distribution doesn't normally make something look simpler or more complex. It just kind of moves the knots around, in my opinion. But right now we're still on the conditional exchange. I like the conditional exchange because it's both not trivial. It's an interesting thing to learn. I remember learning it as a fun fact. Hey, if P then Q is the same thing as not P or Q. But it's also very useful. There are many situations in which you find a disjunction in a proof, and what you need is a conditional, and then you can make one. Or you find a conditional, and what you need is a disjunction, and again, you can make one. Okay, it's a replacement rule you will find yourself using, but not in that pedestrian way that you find yourself using the commutative rule, which after all, you can use really, shall I say, even without really thinking about it. Now we have no disjunction in this one, still a replacement rule involving a conditional. And I mean, it's a little bit silly if when you're teaching logic to have a favorite replacement rule. It seems a little childish, but if you're just asking personally, what's my favorite replacement rule? I'd have to say it's exportation. It can be mysterious, even surprising when you first see it. And then as you think about it and give yourself examples, it becomes obvious. If P and Q then R is identical with, can be replaced by, replaces, If P, then if Q, then R. And as I said, it seems even arbitrary when someone first writes it down. For a minute, you may find yourself thinking, how am I going to remember it? But in fact, all you have to do is come up with one example and it just falls into place. If you're 18 and you're a citizen, then you're eligible to vote. If you're 18, then if you're a citizen, then you're eligible to vote. In both versions of the statement, you wind up at R. R is the consequent. R is where you're heading. And this is a case in which there are two conditions that have to be met for R to come about. Okay, well, the idea behind exportation is you can either group the two conditions together. Are they both here? Then you've got R. Or you state the one condition and say, and then if that condition is met, well then, if the other condition is met, then you've got R. That's all it's doing. If you've got this, then if you've got that, you've got R, which is a way of saying if you've got both of them, you've got R, right? You see, come up with your own P, Q, and R, put them in, see how obvious the exportation rule is, okay? And then I think I can guarantee you'll have no trouble remembering it. It's that straightforward and that's significant. And that too, it doesn't get used as often as the conditional exchange does in a typical proof. But you do sometimes, let's say you're here with P and Q, then R in a proof. You've there, and you want to wind up with a different sort of conditional, one involving Q and R. All right, exportation shows you, as it were, how to export the P. Take the P out of there and leave you with the other condition. As obvious as some of these replacement rules are, or as pleasant to work with, as interesting as, for example, I would say the conditional rule is. You know, I can't say anything like that about the distributive rules. They're complicated and they can take you a while to learn. See that? I already made a mistake writing it down. The first thing you notice about the distributive rules is that they're a little more long-winded this way, but you know, not significantly different. And I would say there's no moment of sudden recognition as you move in either direction. Ah, this is really P or Q and R. Perhaps for that reason, students sometimes find the distributive rules hard to memorize. Well, here's what I do when I have to remember how I remember them. I say, you've usually got, well, you have, if you're practicing the distributive rule, you've got the lone proposition that you're going to distribute over the others. that lone proposition has a connective next to it. It keeps the same connective next to that lone proposition as it gets distributed. So, right, so you can think of the P or as a unit that never gets broken up. So P or Q, P or R. Then how do you remember this is an and? Well, it can't be an or, okay? You've got two different connectives at work in this statement, and you're gonna have two different connectives in the long distributed version of the statement. Here, the P comes right next to the and. And guess what? The P is next to the and here, and the P is next to the and here. It distributes, and then the connective that had been inside comes outside. The connective that had been inside these parentheses now comes between the two parenthetical remarks. How useful is that as a mnemonic? Well, it works for me. It has worked for other people. It has failed to work for some people. Now, in my experience, the distributive rules for truth functional logic only occasionally matter within a proof. And from every example I can recall, they matter only when someone has constructed a proof that's designed to make sure you know what the distributive rules are. Nevertheless, and as with the other replacement rules, and as with the 8 inference rules, it pays to memorize them. Once you can memorize them and remember something like the abbreviation that they are marked with, why then the proof becomes, every proof becomes much more straightforward. It's a lot more work going back and forth, checking out the rules and seeing which of them apply. So that's it. These are the rules by which we'll practice every direct proof using so-called natural deduction within truth functional logic. As I said at the beginning, we could have done a lot of the same proofs with the rules of inference alone. We can be a little more flexible when we also have the replacement rules to go by. Let's do an example or two. And let me start by saying, as I go through and work out a sample proof, you may think of another way of doing the same proof, okay? That's great. Almost any proof that gets assigned in a course like this one, unless it's a trivially short proof, is going to admit of more than one derivation strategy. And although all things being equal, shorter ones are better than longer ones, if the difference in length is just a line or two, I don't find that interesting enough. I think you should just fall into whatever proof you find. Okay. We want to wind up with not A or E. And maybe the letter E is going to be the signal to you, the little cue that we have to see where the E comes from. And we notice there's only one line of the premises. Sorry, these are all premises. Only one of the premises has an E in it, and that premise is a conditional. All right. I'd like to do this proof, although there are other ways. I'd like to do this proof using dilemma. the rule of inference we call dilemma, although we're going to need replacement rules in there too. By conditional exchange, we take the not A or B in the first premise in line 1, and we make it if A, then B. Using conditional exchange again, we take the second premise, line 2, and make that if B, then C. And you can see where this is going. By hypothetical syllogism, applied to lines 5 and 6, we get if A, then C. Now time for a replacement rule. How about the contrapositive? I told you I like the contrapositive. All right. Is that going to help? Well, now we've got a conditional whose consequence is not A. And we already have a conditional in line 4 whose consequence is E. And we want not A or E for our conclusion. So we've got if not C, then not A. If D, then E. And now look at line 3. There are the two antecedents in a disjunction. So this disjunction plus this conditional lines 3, 4, and 8 by the rule we call dilemma. You have two conditional statements. You've got a disjunction of their antecedents. You're going to have the disjunction of their consequence. I don't know about you, but when it comes to proofs in logic, I can't do just one. Okay, so let's try just one more. We'll make it a short one. Here's our first premise, A or B and C. And the second premise is simply if C, then D. And we want to wind up with a conclusion, A or D. A or D, how are we going to do that? Well, remember what I said in introducing the distributive laws. They often only show up in a proof that has been designed to require the distributive laws. And this is one of those proofs. Let's distribute A over the conjunction B and C from line 1. Now, where we have this conjunction, of course, by the rule of inference called simplification, we can have just one of the conjuncts. My apologies. For a second, I forgot what the proof I had come up with here, but now I remember. We turn that disjunction into a conditional statement, right? A or C is replaced by if not A, then C. Now we go back to the second premise. So from this line and this line together, by hypothetical syllogism, we get if not A, then D. And then we come to the conclusion by, again, applying conditional exchange. I love the fact that for a few seconds there, I completely blanked on the proof strategy I had come up with because I had jotted down the problem for myself and I thought, nah, it's pretty trivial. And then it wasn't quite trivial enough. What I like about that is I hope that enough proofs are going to work like this that you're not sure how to go forward. And then once you see the way forward, they really unfold and you realize in the end, there's nothing to them. Okay, that's what you can do. That and much more is what you can do when you have the rules of inference together with the replacement rules. And that's enough for now.